We would like to talk about the limit of a function at a given point. And maybe one way to uh, find the motivation in order to introduce this is the very definition of the derivative of a function. So we define the derivative of a function as the slope of the tangent to the graph at a given point. So you have a graph of the function y equals f of x, and we have a point a comma f of a, and we could informally define the tangent to the graph at a given point as the line that goes through that point and seems to be matching the graph in the best possible way. However, the very description that we just gave, that is match the graph in the best possible way, cannot be considered to be an absolute description. It's just a very, very intuitive description. You ask 10 different people to sketch a line that matches the graph at that point, and you're going to get 10 different answers. So the question is, how can we make that concept much more well-defined? And the answer is, we simply don't begin with a guess as to what the tangent is going to be like, but instead we pick up an adjacent point, or a point close by, if you will. Let's call this point x comma f of x. And what we do is we draw the secant line between the point x comma f of x and a comma f of a. This is a well-defined line that has slope. So this is the slope of the secant. Which will be rise, which is f of x minus f of a, the difference in y's, overrun the difference in x's, and that would be the slope of the secant. So now, our approach to the slope of the tangent is to try to imagine that the point x slides toward the point A. So here's the point A, here's the point X. X slides toward A, actually both from the left and from the right. And the limit as x tends to A of f of x minus f of a over x minus a will eventually be the derivative of the function at the point A. So it will give us the slope of the secant. And of course, once we have the slope of the secant and we know that it goes through the point A comma f of a, the slope of the tangent, then we will have the full equation of the tangent itself. And now, how would we define the limit of a function? The limit of a function has to be defined in a rigorous way, but we're going to simply avoid doing that. And the definition follows pretty much the patterns of the definition of the limit of sequences, but we have already examined how that definition is given, and we're going to simply avoid giving this definition. Instead, we're going to pretty much see that for all common functions that we're going to be interested in, as long as you can plug in, that will be the limit. Meaning, if you have a situation where you want to find the limit as x tends to 3 of x squared plus 1 over x minus 2, then you can see that you can simply plug in 3, and that will give you 10 over 1. Now, what happens in situations that you cannot plug in? We will have to consider those separately, but it would be interesting to actually make a small demonstration of such a case. So imagine that we were looking to find the slope of the tangent to the graph, meaning the derivative, at the point, let's say, So this is y equals x squared, and we're interested in the point 2, 4. So this is the point 2, 4. And according to what we said, this would end up being the limit as x approaches 2 of the rise, which is x squared minus 4 over the run, which is x minus 2. And we would be interested in finding this limit. And clearly, this is a situation where we're not able to plug in. Because if we plug in, we get 0 over 0. So the intuitive approach to limits tells us that what we need to do is start plugging numbers very, very close to 2 and see what we're getting this way. So for example, if we plug in x equals 1.9, then we will realize that we get 3.9. If we plug in 1.99, then we will get 3.99. If we plug in 2.0001, let's say, we're going to get 4.0001. And as we keep plugging in numbers that are very, very close to 2, we will see that we'll be getting numbers that are very, very close to 4. That is, in some sense, the first intuitive approach to the notion of limit, but it is exactly the French School of Mathematics that gave the final definition of limit the way that it was used and to develop mathematical analysis in the 19th century. Now, as we're going to see, in our case, we will have some very interesting resources. So in a case like this, for example, one way to resolve the situation that we're looking at is to actually apply a simple algebraic trick. So we see that exactly because the numerator becomes 0, we can actually factor out x minus 2, and that will give us x minus 2 times x plus 2 over x minus 2. These two things cancel each other, and we get to a situation where it seems that we should be able to plug in. And if we plug in, we find 4, which aligns perfectly with the little table that we had on the top. So in other words, and we can come up with situations that do not involve the derivatives. One, for example, could look at something like this: the limit as x tends to 1 of x cubed plus x minus 2 over x squared plus x minus 2. And again, in this case, we have 0 over 0. And here, for example, one would simply use synthetic division in order to come up with a much more favorable case. So if I use synthetic division for the top, let's say, then I will have 1, 0, 1, negative 2. I put 1 here, and this will give me 1, 1, 1, 1, 2, 2, and 0. So this will end up being the limit as x tends to 1. So on the top, we just found x minus 1 times x squared plus x minus 2. And x squared plus x plus 2, actually. And on the bottom, we can, again, do a synthetic division. Let's see what we find. So we have 1, 1, negative 2, 1 here, put 1 down. That will bring us 1 here, 2, 2, 0. So this will be x plus 2. And now we have a life-saving cancellation. And once we do that, then we come up with a limit that we can actually compute by just plugging in. So we should consider still the concept of plugging in order to compute a limit as something tentative that needs a little more discussion, a little more explanation. But the rule of thumb is that for simple functions that will come our way, we will always be able to do that and compute limits this way, even though it needs to still be discussed what are the functions for which one can compute a limit by substitution is possible. And we're going to very soon look at many more algebraic tricks that allow us to compute limits, but that's pretty much our introduction to the notion of limit.